Assalamu alaikum dear students. This is our next problem. Problem once again having been chosen from the book Modern Physics by Kenneth S. Crane. This problem is about Wein displacement law. Okay. First we come towards this statement. Okay. The surface of the sun has a temperature of about 6000 Kelvin. Okay, dear students, here one thing needs to be clarified, that usually when we take temperature in Celsius or centigrade, then we use degree. Okay, degree Celsius or degree centigrade. Similarly, when we take temperature in Fahrenheit, we use it in degree Fahrenheit. Okay, but when we use temperature in Kelvin, we do not use the term degree. Okay, 6000 Kelvin. At what wavelength does the sun emit its peak intensity? How does this compare with the peak sensitivity of the human eye? Dear students, here actually we will take into consideration electromagnetic spectrum. Okay, we move to its solution, then we will discuss what is actual position. Okay, first we come towards helping tools. Okay, tool number 1 is about the definition of Wein displacement law. Okay, Wein displacement law for a black body. Okay, dear students, in this problem I have taken snapshots from two different books just in order to make a comparison between these two snapshots. Okay, if we include more books, then slight negligible difference may seem to appear, but actually there is absolutely no difference. Okay, all books convey the same sense, only their style may be slightly different sometimes. Okay, anyhow, we define Wein displacement law for a black body. Okay, first we take the first snapshot. Okay, I do not remember from which book this snapshot has been chosen. Okay, because I have hundreds of books. Anyhow, Wein displacement law for a black body, according to this book or this snapshot, says that wavelength lambda m into temperature T is equal to 2.90 into 10 to power minus 3 meter dot Kelvin. Okay, where lambda m is the peak wavelength in spectral emittance curve. Peak or maximum is same sense. Okay, lambda is usually for wavelength and m is for max or maximum, and maximum and peak are almost equivalent terms. Okay, while T is the absolute temperature of black body. Okay, so 2.9 10 to power minus 3 is called milli. 10 to power minus 6 is called micro. 10 to power minus 9 is called nano. 10 to power minus 12 is called pico. 10 to power minus 15 is called femto, etc. Okay, we can pronounce it as lambda lambda t equal to 2.9 millimeter dot K, absolute temperature. Okay, K. Or now we take into consideration Wein displacement law as described in some other book. In the other book, the exact 100% same definition, but we see what difference seems to appear. Okay. Wein's law relates the temperature T of a black body radiator and the wavelength lambda max at which the spectral radiancy is maximum. Lambda max into T is equal to 2898 micrometer dot Kelvin. Okay, here what is the difference? The difference is no difference, but apparently we may say that it looks like perhaps there is a negligible difference, but actually there is absolutely no difference. Okay, the only difference is that here lambda m is written as lambda max. Okay, no difference because m is also for maximum or peak. So in this expression, in place of simply m, max has been used. Okay, and t is same. However, dear students, the only difference is that here in place of millimeter, micrometer is used. Okay, micro means 10 to power minus 6, nano means 10 to power minus 9. Okay, when micrometer will be taken, then we will not write 2.90, it will become 2898 micrometer dot Kelvin. Okay, if we rewrite this second form in shape of first form, then what we will do, we will write lambda mt is equal to 2.898 into 10 to power minus 3 meter dot K Kelvin. Okay, what we will do, we will write it as 2.898, and we know that 2.898 will be rounded as 2.90. Okay, anyhow, these things are of very basic level, we do not need to waste time. Okay, dear students, in tool number 2 we have taken into consideration table regarding electromagnetic spectrum, wavelengths of visible light. Okay, dear students, here again a minor difference will appear, but actually almost no difference. Okay, one more thing which I intend to point out here, that to the extent I remember that when I studied this law many years earlier, when I was in my school life, then I remember that after violet, indigo color was also included, and at that time, what time, about 1981, 82, 83, 84, etc. Okay, I had made a word just in order to remember this arrangement. I had remembered the word vibjoyer. Okay, vibjoyer. V for violet, I for indigo, B for blue, G for green, Y for yellow, O for orange, and R for red. Okay. At that time, I had remembered this arrangement in the shape of a self-made name, vibjoyer. But here I am slightly surprised why indigo has been excluded from that word. Okay, there are 1, 2, 3, 4, 5, 6. There are 6 colors. Okay, seventh color definitely that color may be included within this range because nothing is left from 380 to 750, and in the alternate expression from 400 to 700. Okay, all wavelengths are included, just their classification is different. That for violet this is from 380 to 450, for blue from 450 to 495 nanometer shows point. Okay, so dear students, here slight difference seems to appear, that here wavelength range starts from 380 and ends at 750, while in second table it starts from 400 and ends at 700. Okay, so despite this minor difference, we should not go in such unclear discussion. At some later stage this point will become clear for us. Okay, anyhow, I want to say that there is absolutely no difference in above two various types of tools, two forms of tool number 1 and two forms of tool number 2. Okay, everything tallies with the other relevant or corresponding value. Okay, now we come toward its solution. Okay, we know from Wein displacement law that lambda max t, okay, maximum wavelength, peak wavelength lambda max into temperature T is equal to 2.8978 into 10 to power minus 3 meter dot Kelvin. Dear students, if we see that, we can conclude that this value actually do not correspond with either of two shapes given in my toolkit. There is a very less difference in this value perhaps. Actually, the reason behind this is that I have chosen this value from the original book which we are here following, that is Modern Physics by Kenneth S. Crane. Okay, in the book Modern Physics by Kenneth S. Crane, value this is given. Okay, instead of 2.9 or instead of this value 2898, this is not 2898. Actually this is also 2.898, because here after 7 the digit is greater than 5, so when we will round it, it will become 2.898. but the only difference is that here after decimal, four decimal places have been chosen, otherwise no difference. Anyhow, lambda max, maximum wavelength, peak wavelength lambda max is equal to 2.8978 into 10 raised to the power minus 3 meter dot Kelvin divided by T, temperature T. In the next step, we are just using the value of T, which is 6000 Kelvin. Okay, so here Kelvin will be cancelled out with Kelvin and we will be left with meter, wavelength meter. Okay, so after simplification, lambda max or peak wavelength or maximum wavelength becomes equal to 2.8978 divided by 6000000. Actually 6000 is already available in the denominator, and this 10 to power minus 3 in the numerator. When it shifted to denominator, it will become plus 3 in the denominator. Okay, so 6000 multiply with the 10 raised to the power plus 3 will take this shape. Okay, 6 and 6 zeros. Okay, so it becomes 4.8297 into 10 raised to the power minus 7 meter, and I have already mentioned that 10 to power minus 7 is not appropriate for us just as a fashion, as a pattern, as a formality. So we prefer to convert it either into 10 to power minus 6 or 10 to power minus 9. So in order to convert it into 10 to power minus 9, we will convert this factor, that is 4.8297 into 482.97. Okay, that is point will be shifted to decimal places ahead, and then in place of 10 raised to the power minus 7, 10 raised to the power minus 9 will appear, and we know that 10 to power minus 9 is nano, denoted by n, so it will become equal to 482.97 nanometer. So our one part has been solved. Now we come towards its range. Okay, so in response to remaining part of the problem, we just say that we know that wavelengths of visible light range from 380 nanometer to 750 nanometer, and hence 482.97 nanometer is almost in the middle of visible spectrum. Okay, what we have done actually, dear students, here we have taken into consideration one of those two tables which we have shown in our toolkit. Okay, because one table is from 400 to 700 and one table is from 380 to 750. Okay, this is from 4 to 700. Okay, we have not taken this, we have taken this, that is from 380 to 750. Okay, so we have taken this range, and when we compare this with this, we come to conclude that this is in between, almost in between these two extremities. Okay, initial and final value. Okay, so this is the end of our problem. Till next problem, Allah Hafiz.